I'm going to go and look at all the bits and pieces that we haven't covered yet, the situations that we haven't done. The first one I'm going to do is a continuation of yesterday. We're going to do the general algebraic method, right? So that involves us taking an integral. The one I'm going to pick is 13. Did I do 13 last time? I doubt it very much. I'll write it down and you can tell me, yeah, I remember that. If not, that's fine too. We can move on. Right. Did we do any that looked like that right at the end of yesterday? Does that look fresh? We haven't seen it. Great, perfect. Okay, so this guy is obviously a rational function. First stage, you would do no matter what method you were going to use. And you'd pull out x as a common factor. And you got that guy. Agreed? Now, do you notice it's got an x squared term? And when you say an x squared term, does it not mean you cannot use the cover-up method? You have to do the general algebraic method, right? There's no way of avoiding it. So that's the method that I'm going to use. And you don't get a lot of examples of this one. So this is going to be my second and final example of that. Now this guy is going to split as an a over x plus a bx add c over x squared plus 6. And so we're just going to figure out how to do the partial fractions of this rational function. So far, so good? Right. Now, when you do the general algebraic method, you don't cover up anything. Essentially, what you do instead is that you take these two and you put them back together again. So I'm going to multiply the first fraction by a special version of 1, x squared plus 6. And the second fraction, I'm going to multiply it by x over x. And now I have a lots of x squared plus 6 plus bx add c x all over x squared plus 6. And on this side, we still have this guy. So far, so good. Are we good? Any mistakes? Because you know what I'm like. It looks good. Put a little bracket around it. I don't know if that helps. Right. Now, these two are equal. The bottoms are the same. That means that the numerators are also the same. And we are now at the point where we have this quadratic is equal to this. And the cool thing is that no matter what value of x you pick, this side must equal that. And now we go choosing x's. And the trick is, if it's possible, and in this case it is for a little while, and then later on it's not, you try and choose an x that makes, in this case, 2 of the variables disappear on you and only leaves 1 behind. What would be a choice of x that would do that type of thing? What could I make x equal to that would 0? Would you agree? Now, if you make x 0, you get 0 take away 0 plus 36. So that's 36. If you make this 0, 0 add 6 is 6, so you get 6a. And if you make this 0, the whole thing is 0. And guess what? You now know a. Okay. So once we know b and c, we're done, right? Now, this one has a little kick in the tail because these questions are kind of, depends on what you get, what you have to do. Yesterday, we managed to get away with choosing a value of x that would then get you the b, and then you choose another value of x, any value you like, and get c. Right now, I'm rewriting the information and I'm replacing the A with 6. So it's 6 lots of x squared plus 6 plus bx add c times x. Now, in this particular situation, we have a problem. And the problem is I can't really choose a very good value of x that is going to make one of these two guys disappear. Would you agree if I choose x equals 0, doesn't all of this disappear and I get nothing out of it? But that would have been the candidate if this hadn't been x. See, if this had been x plus 1 or x minus 2 like yesterday, my next choice would be x equals 0. So I'm going to show you two different techniques for getting B and C. First one is maybe not obvious, but let's see what happens. I'm going to distribute everything. I have 6x squared, I have 36, I have bx squared, I have cx. Now, if we collect like terms, I have 6 plus b worth of x squareds, I have a cx, and I have a 36. And over here, I have that. Sabrina is nodding in the way that means, I think I know what you're going to do, nod. I don't know if I'm right or not. Okay. If you look at this has to be the same as that, doesn't that mean that cx has to be the same as minus 1x? Is that what you were thinking, Sabrina?
I was actually just looking at that 6 and b together and thinking that.
Ah, okay. So what did you think about the 6 and b? What does it have to equal?
If b was -6, we'll get rid of it. No, wait, we need x. I don't know. No, I was.
Oh, well, you're kind of on the right track. Isn't this has to be the same as that? So doesn't this have to be 1? And the one I was looking at that attracted me is, isn't that C has to be this guy? So doesn't that make C -1? Hey, we know what C is now. Now, not 0, but you change your mind quite rightly. What is the value of B that is going to work?
Would it be -5?
Correct. And now you're finished. Do you see that you found the B and the C? So we have A, we have B, we have C. So that means that this fella here can be written as A, which is 6 over x, and a B, which is -5x, and a C, which is -1, all over x squared plus 6. Haven't we done what we set out to do? Haven't we got the two partial fractions? Right? A, B, and C. Now, we want to integrate this guy. Right? We want to integrate this guy. What I suggest you do in all these questions is separate them out. Separate them out like this. Each one of these pieces we can then integrate separately. This guy is 6 natural log of x. Do you recognize from yesterday what 1 over x squared plus 6 was? From yesterday, the integral of 1 over x squared plus 6. It has an inverse tan in it. Come on. You know you want to tell me the answer. What does that 6 get you?
Is it the square root of 6?
Yes, 1
Oh.
over the square root of 6, x over the square root of 6. Now, what do you think we are going to do about that middle one? Right, we still have to figure out the integral of 5x over x squared plus 6. How are we going to get that answer? What method will I use to get the integral of 5x over x squared plus 6?
Is it u sub?
Correct. What's the u sub going to be?
X squared plus 6.
And you are going to just trust me on this. Eventually, after a few lines, you end up with negative 5 halves, the natural log of x squared plus 6. You've got this guy. And you are finished. Oh, now you're finished. Okay, so you just trust me, if you do a u sub, that's what the middle term eventually becomes. Now, I promised you 2 methods, and I would intend to do that. We're still going to get the same answers, of course, because it's the same fella. So I'm going to kind of start at the line that looks something like this. Right. And the technique that we went and used to find it, right, was well, it's gone now, whatever the damn thing is, but wasn't it? Is basically there it is. It's equating the coefficients. But what we're going to do this time is we're going to still do the choose thing. Now, if you cannot pick an x that leaves you with just one variable, this technique of choosing the x values can still work. Just pick any two numbers you like for x. Just don't pick 0 again, right? And being lazy, I'm picking 1, because I figure out if I pick the number 1, it's probably going to be nice numbers, right? So if you choose x as 1, you get 1 squared, take away 1, add 36. 6 lots of 1, add 7, that's 42. And this guy becomes b times 1 times 1. Are you happy about when you choose x equals 1, this expression becomes 42 and a b plus c times 1? Are we good with that? Now, if you take away 42 from both sides, you're left with negative 6. And you have got essentially a system of equations. All you know right now is that b add c is negative 1. And then you choose any other guy that you like. And my suggestion to you is, provided this guy isn't 1, which it won't be, pick x equals 1, and guess what you should pick for the next one? Read my mind. What do you think?
-1?
Yes. I suggest strongly that you pick those two. And hopefully you'll see in a minute why that's a good choice. -1 squared is 1, that's 38. -1 squared is 1, so you still get 6 times 7 is 42. And this guy is a little bit messy because he is negative b add c times -1. So what we get is 38 is 42 plus b take away c. And if you subtract 42 from both sides, I believe you get -4. And I'm going to call that equation 2. So I'm going to write these two equations next to each other. I know that b plus c is 6. And I know that b take away c is -4. Somewhere in your math career, you learned how to do things called systems of equations. Can you remember those guys? ND 94, 99, if you took math here. I don't know where it would be in your high school life. Those two equations, because of these choices, aren't they very easy to solve? I'm going to use what's called the addition method, which says you can add them together. So 2b is -10. So that makes b -5. And guess what? Isn't that exactly what we got? Now, since I know that b is -5, can't I plug it into b add c is -6? So -5 plus c is -6. Doesn't that tell me that c is -1? We've solved it. Do you see then that that was two quite different techniques to finish the problem, right? Two different ways of finding out what b and c is. And I can pretty much bet a bottom dollar that there's probably 2 or 3 other techniques that you might have came up with that might have got you the same result, right? Guess and check, dangerous, but you might have got lucky, right? But cool to do it. The technique that was done here was actually suggested by one of my students from the other class, which I thought was really cool. If you want to look this up, it's called equating coefficients. This process where you've got a polynomial equals another one, but some of the coefficients are variables, or like a and b and so on. It's called equating the coefficients. Right, that's it. That is all we can do, all I'm going to be able to have time to, at least, to do on the general algebraic method. Would you agree it's much vaguer, it's much more clunky, you know, it involves a lot more work, right? So you avoid it whenever possible. So now we're going to look at some tidying up loose ends. So here's the first loose end. One of the questions, I think it's 1b or 2b, I can't remember exactly the number, asks us to write down what the partial fraction for that guy would be. Well, the first thing you do is you break it apart like that guy. Agreed? You factor it. You do that every time. Now, this fella here, I'm going to call it cx plus d. And the other guy, the x squared, he gets ax plus b. I'm not finished, but I'm there. If you have a square term on the bottom, you always have one less than it on the top. So ax plus b. You got a square term, cx plus d. Are we happy about that? Now, what you do with the x squared is something you do that's different from this. You rewrite this as ax over x squared plus b over x squared plus c x plus d. You split the x squared. So if you ever have x squared, you split them. And the reason you split them is that you have an a over x, a b over x squared, and a cx plus d over 1 plus x squared. I don't know why I put brackets around that, but I've done it now. This is the partial fractions for that. You are never going to get this as a question, but imagine that you got, start again. Suppose you get x cubed x plus 1. That would get you an ax, a bx squared, a cx cubed, plus a dx plus 1. Can you see how the partial fractions split for the x cubed? Suppose you've got an x cubed plus an x squared plus 1 and an x cubed plus 4. The two terms that you're going to deal with are those guys. This fella is an ax plus b. What would this guy get you? What would you put on top of an x cubed plus 4? Any ideas? I know you haven't seen this, but what do you think it might be?
Cx squared plus d.
Almost. So the generic rule is, don't you put a polynomial 1 degree smaller than the guy that's on the bottom. Try to phrase that in a way that makes sense to me, right? So an x cubed in the bottom generates a quadratic. Are we good with that? Right. And the last thing that I want to deal with then are what do you, or how do you deal with questions like this? Now, I know there's two of them, so I want you to actually maybe pick something similar to the question that I'm dealing with. That comes later. Here we go. This is like question 11. And it's, how do you deal with guys like that? Now, superficially, you might say, oh, that's a nice, easy one. It's going to be the cover-up method. But the answer is no, you cannot use the cover-up method. And the reason you can't wasn't one of the rules is the top has to be smaller per degree than the bottom, right? Isn't that a T and so that's a D? So you can't do it. Now, I was pleasantly surprised that a student figured out a trick, some other way of writing this fraction that is eventually going to allow us to simplify this fraction into something else that we can do, something else that we can integrate. Now I've got 3t minus 4. I'm not allowed to change what it is equal to, but I am allowed to change how it's written down. And I'll give you a clue. It starts with a 3t. Have you got any ideas of how he figured that out? Which I think was pretty amazing because nobody told us, right?
Could you maybe rewrite it as like 3t to like the 1/2 or something like that?
Oh, interesting. You do rewrite it, but not the way that you said. But yeah, you're on a kind of track that you rewrite 3t minus 4 in a very specific way.
3t plus 3 minus 7.
Now, why? This is correct, Matthew. Why is that any better than the thing we started with? Would you agree it's still 3t minus 4, right? It's still the same guy. Well, if I split it into two distinct pieces, look at this guy for a minute. This guy can be simplified, can't he? 3t plus 3 over t plus 1 can be simplified. Since Matthew knows the answer, he's not allowed to answer. What could you rewrite 3t plus 3 as that's going to be of help? 3t plus 3.
Put it on times t plus 1.
And would you agree that the t plus 1s cancel and you're really just integrating a 3? And then you're integrating this guy. And that gets you 3t, and that guy gets you 7 log. Now, do you notice that that method had nothing to do with the cover-up method, and it had nothing to do with the general algebraic method? Would you agree this is just a random question that you had to figure a way to solve it? Isn't that sneaky? But cool. Now let's give you another one to try out. How are you going to rewrite the top? You can't change the 4x. So I'll just write that down. I know Matthew knows the answer because he's smiling far too much. But
Would
he's
it-
not going to, yeah,
Would
Caitlin.
it be 6 minus 4?
Yes, it would be. Now, if you take it to the next stage, see, once you've seen one of these, can't you like say, hey, I don't know, I've turned that into a T. I can do this guy kind of the same way. How are you going to deal with the top fella? How are you going to rewrite that? Four x add 6. How's it going to be written?
2 times 2x plus 3.
Are you beginning to see a theme here? And you know, dot, dot, dot. Look at the top and look at the bottom. Don't play with the bottom, but say to yourself, okay, wouldn't I like the top to be a multiple of that? Right, so this is in my brain what I'm saying. Okay, 2x. Well, if I doubled it, I would have 4x add 6. But that's too much. Well, if I take away 4, I can get my 2 back. Up here, right, I've got a t plus 1. Well, I would like to get 3t. So, well, okay, 3t plus 3. Okay, 3t plus 3. Well, that's not right. I need to take away 7 to get back where I came from. Cool. Now, this is a very, specific technique for a very specific question, right? Every question that is got a guy in the top that's bigger than or equal to the one on the bottom, you have to figure out another strategy, right? A way of doing it. And this is the last question. This one is different again. So we're going to have to recreate a method for doing that guy. Now you notice the top is x squared this time. I mean, if it'd been x, I could have fixed that one pretty easily, right? I would have just said x take away 6, add 6, and I'd be finished. But this is x squared, so forget how you do this, because this isn't going to be the method. Come up with a different way of tackling this fella. Totally unconnected with this method. And you did it in 141. And you did it when you were sketching rational functions. Actually, you did it just before you sketched them. Any takers?
Is it gonna be minus 6x plus 6x?
Do you know, Caitlin? I wasn't expecting that answer, but that actually could work, but I'm not going to do it that way. So I like your thought process. That actually could work eventually. Any other suggestions? So hold that thought. It's a good one, but it's not the one we're doing.
Could you do like polynomial division?
Yes, you do. It's called, well, in some cases, it's called long division. Can you remember doing long division in 141? I think it's roughly in about the middle, right? I bet you thought after you did the 2 questions that you probably did in long division, well, that's it. I'll never need to worry about long division again. We're never going to see that. Well, guess what? You're about to see it. So here goes. You look at this guy and you look at this guy and you say, what do I need to multiply x by to get x squared? And the answer is x. You then take that x and you multiply these 2 terms and you get x squared take away 6x. And then the last thing you do is subtract. X squared take away x squared, nothing. Nothing take away negative x gets you 6x. And then you start all over again. What do you need to multiply x by to get 6x? And the answer is positive 6. You then multiply this by positive 6 to get 6x. take away 36. And to finish, you subtract. 6x take away 36, gone. 0 take away negative 36 is add 36. Now you can stop. Because what we have is that this thing is x plus 6 with a remainder of 36 x minus 6's dx. And this guy you can integrate as a half x squared. This guy you can integrate as 6x. And this guy you can integrate as 36, the natural log of x minus 6 plus c. And you are finished. Would you agree that is nothing really like this one? If Caitlin's got time, she might want to work on what she was doing, and you're about halfway through and you have to figure out a way to finish it. But that technique that you mentioned would work. We are done for this section. We are now moving on to a special section. This section has it has homework, but there is no grade given. So you can choose to, okay, excuse me a minute, I haven't got the window on. You can choose to do some of this homework, none of it, or all of it. It's basically giving you, darn it, I can't get my windows open. Where are you hiding? I think you're hiding here. You are, good. So it's strategies for integration. I'm going to show you presently once I get all the windows opened and closed that I need to. And it's basically practice on every technique that we have done. And it's good practice. And I strongly suggest that you do as many of the questions from this homework, which is 0 points. So in other words, if you do it and you do every single question correctly, you get 0 out of 0. And if you do none of them, you still get 0 out of 0. And so what's the problem? Or what are we dealing with here? Let's make it a little bit bigger. There we go. Right now, you have seen a large number of strategies, techniques for finding integrals. But the problem is that for the most part, you knew what you were going to do. Didn't you do a section where everybody was U subs? So you knew it was going to be a U sub, right? Or you did X subs. Well, you knew it was going to be an X sub, right? Or it was an integration by parts, or it was a rational function, right? That's these guys here. Number 5, no particular order, good memory, I'm calling it. Aren't there some guys you just know what the answer is because you've memorized them? Don't you know that the integral of 1 over x is natural log of x, right? Don't you know the integral of cosine x is sine x? How do you know that? Because I've got a good memory and I memorized it. Evidently, some of you haven't got as great a memory as I would like, but you're going to prove me wrong now. For instance, this one is just done by having a good memory. What is the integral of 1 over 9 plus x squared?
Tangent inverse.
1/3 inverse tangent x over 3. Remember? 1 over a squared plus x squared, right? And for completeness sake, don't we also know the power rule? Right? So what you're going to now do is we're going to go through a lot of questions, as many as I can today, and tomorrow a lot more. And we're only going to do what method? You will finish the method off yourself, as extra practice. Right. Let's look at the first one, question 1a. What technique will you use to integrate 4x over 1 plus x squared?
U sub.
Correct. What's the U sub going to be?
1 plus x squared.
Nailed it. What about question B? Do you
That's memorization.
recognize it?
That's the tan inverse.
Yeah, it's an inverse tan, right? A good I've got a good memory one, that one, right? C is going to catch you if you're not careful. What technique will you use for C?
X substitution.
Not this time, no. If it was, well, no, actually, I can't think of a situation where that would be. Okay, if you factor the bottom, call it 1 minus x, 1 plus x, isn't that the cover-up method? Right? 1 over 1 minus x, 1 plus x. It's two linear guys, cover-up method of 4 over it. Question A. It's not so easy, is it? When you don't know the method, right? When all you've got in front of you is a question and you're scanning through what techniques am I going to use? What would you use for A?
That's the inverse cosecant there. No, sorry, that's
Keep going. What would it be instead? Something else. 4A.
U
Would it
sub?
be integration
U
by
sub.
parts?
No, U sub is good.
Oh, yeah.
And what would the U sub be?
X squared minus 1.
Correct. What method would you use for B?
memory.
If that X was gone, it might be, but it's not. But I like the fact that you're trying, and that's important that you're making your mind work.
So
Do you
that
reckon?
one would be integration by parts. 'Cause
No,
the one- No?
no. Okay, I'm about to tell you, it's an X sub. Why is it an X sub? Do you know the X subs with the horrible x squared plus 1s and 1 minus x squared? It's one of those guys. I believe that one's secant theta. What about question C?
X sub?
X sub?
Yeah.
Yeah, I would go X sub. Okay, what about question A?
Would that be integration by parts?
No, but I understand why you chose that one.
Is it
U
U
sub?
sub?
It is. And who's the U sub going to be?
X.
ln of x.
Are you sure? Not X, no. What's the U sub going to be?
ln of x.
ln of X. Okay. Question B, so I don't make your life hard, is actually just basically, you could say a U sub 2x if you wanted to, but I wouldn't. Isn't that going to be integration by parts now? Who is the f of x going to be in that question?
Natural log of 2x.
Yeah. And if you do question C, what method are you going to use?
U sub.
Nope.
Also integration by parts.
Also integration by parts. It's okay for the same question to use the same method twice, right? Now, when you look at them, don't they look very similar? But, well, let's take A and C, right? They look very similar, would you agree? But where the X goes does alter your technique, doesn't it? So it's the little nuances that make the difference, the little differences that tell you. Right, 4A, I'll put this one out to you. You've done 4A already, haven't you? I remember this guy, or at least somebody like him. What method did you use? because it isn't even in my list of 6.
Just trig substitution.
No, so, well, trig identities,
Or
but that
trig
might be what you mean.
identities.
Yes, I agree. You would turn it into a half 1 minus cosine of 2x. It would be a trig identity. What would you do in question B, however?
You'd break it apart, so then it would have to be an integration by parts.
Breaking apart is good, but I wouldn't do an integration by parts. I would break it as a sine and a sine squared. Wouldn't that be just one of the a u sub, right? With sine x or cosine x, whichever. What would you do in question C?
U sub.
Yeah, if you wanted to, 2x, or wouldn't the answer just be a half cosine of 2x and then the half and the 2 cancel? But yeah. Okay, what about this one? Question 5.
U sub?
Correct. What's the u sub?
Is it just sine x or is
Or
it cosine x? Or is it 3 minus sine x?
it's 3 minus sine x, isn't it the entire denominator?
Oh, okay.
Right. Now let's pause for a minute. Can you see how hard it is now to do these questions when you don't have the framework? Oh, it's an X subsection, so it must be an X sub. You see, now you have to go into the big bad world where nobody tells you who it is, right? You're looking at it and you have to choose. And that is a skill that you will definitely get as time goes on. I mean, right now it's a bit cruel because we haven't practiced at looking at them. So you're kind of being chucked right into the deep end. But hopefully you're getting into the swing of it. What would you do in question 6? What method?
Would you do integration by parts?
Correct. Who would you make f of x?
Log natural.
Yep. What would you do in question 7?
U sub?
Correct. Now be careful. Which u sub?
2x plus 1?
Correct. Oh God, this is a good one. Oh, this is sneaky. You get brownie points if you can tell me this one.
Will it be the rational functions we just did and we have to split it into the partial fractions?
I see where you're thinking. Since there's only one term in the bottom, unfortunately, no. But I do see where your thought process is going. It's not a bad thought process, but it's not the one that's going to work here. I could give this question to my Calc force. Well, I don't have a Calc 4, I have a Calc 3, but next quarter I'll have a Calc 4. I could give this to my Calc 4, right? These are students who've been doing, 3/4 of calculus, so they should be pretty good at it, and a half of them wouldn't get this. Last chance, and then I'll tell you, because it's a sneaky one. Going to do a u sub, but the u sub isn't even x to the 4 plus 4, which is what you would expect it to be, right? It's not going to be x to the 4 plus 4. It's going to be x squared. And what happens is that the bottom turns into u squared plus 4, and I think the top turns into a half. So you end up integrating a half of u squared plus 4, which is an inverse tan. That is a sneaky question, but sneaky is good. Another brownie point question coming up. Any ideas of how you could do that one? In fact, I'll give you 2 brainy points for this one. It's even worse than the one I mentioned before.
Would you just do integration by parts and then have to do like a U sub to get rid of that sine times cosine? Because that would be the G.
That is so cool, Kyra. And it is not the way I was going to do it. But that
Darn
was
it, I just love integration by parts apparently.
yeah, but that was good. That actually would work. I mean, this question would take you forever to do, but your strategy would have worked. The sine cosine x thing, you could do that in a number of ways. You could call it a half sine 2x, that would work. Or you could just do a U sub on it separately and that would work. But that is a very good strategy. Yeah. Not the way I would do it, but I'm keeping yours because yours is actually better than the way I was going to do it. Sometimes the answer is obvious, not because it's obvious, but because there's only one thing you can pick, or maybe 2 things you could pick, and only one of them works. So what do you think you would do in question 10? It's got a look to it that kind of makes it has to be this method. Even though you're not quite sure how it's going to work out, you have to kind of trust the math. What method do you think it has to be? Just the way it looks.
U sub
Yeah. And who's the U sub going to kind of have to be?
1 over x.
Yeah. Trust me, eventually it works. I mean, you have to do other stuff, but that's the start. Do you recognize question 11? And you better say yes. Good. Isn't that what we just did today? Isn't that one going to have to be x squared plus 3 on the bottom and the general algebraic method? What about question 12? Oh, last one for today. Question 12.
Is it x sub where you would substitute like tangent at the bottom?
Yeah, it's an x sub. I think it's secant, but that's not a big deal. You got the hard part done. It's an x sub. And then it turns into what it does.